So we're continuing our study of finite fields. Let P be a prime number. Then I claim that the splitting field for the polynomial x to the Pn power minus x, that's a polynomial with coefficients in the field Zp. That's a finite field that contains p to the n elements. So what the theorem here says is that for any prime p and for any positive integer n, a finite field with p to the n elements actually exists. So let's prove this theorem. So not only does a finite field of this size exist, I'm telling you exactly what it could be. It's the splitting field for this polynomial. All right, so we have the derivative, the usual calculus derivative of this polynomial over Zp is p to the n power x to the p to the n power minus 1 minus 1. Now I'm in the field Zp. The characteristic is p. So every time I have a p, that's actually the 0 in the field. So this is just negative 1. So the derivative is simply the constant negative 1. So f and the derivative, f prime, do not share a divisor of degree bigger than or equal to 1. The derivative doesn't even have a divisor of degree bigger than or equal to 1. We proved a statement that said this condition is true if and only if f does not have a multiple root. So f does not have a multiple root. Now, I'm considering the splitting field for this polynomial. So in that splitting field, my polynomial f can be expressed as x minus alpha 1 times x minus alpha 2. The splitting field is the smallest field that you need to write your polynomial as a product of degree 1 terms, linear terms multiplied together. This is a polynomial with p to the n power roots. So when I have this factorization over the splitting field, I have these roots going from 1 up to Pn minus 1. All of these elements here are in the splitting field. Let's say that splitting field is F. Okay, none of these elements, alpha 1, alpha 2, and so on, can be the same because F does not have a multiple root. Thus, the elements alpha 1, alpha 2, up through alpha p to the n in the splitting field are distinct. So the roots of this polynomial are all different. I cannot have a multiple root. And I have the right number of roots. I have p to the n elements, so here I have a list of p to the n things. The only thing I need to do to finish the proof is show that I don't need more than these elements to create a field. So I'm considering the roots of this polynomial, but maybe the set of these elements is not a field, in which case I'd have more than I need in my field F. That doesn't happen, and I'll show you why. So let alpha and beta be two roots of the polynomial f of x. So pick alpha and beta to just be two elements in this list here. then let's do this. Let's consider f of alpha times beta. Actually, let me do alpha times beta inverse. Let's see what happens here. So if I look at f of alpha beta inverse, I'm going to plug in alpha beta inverse up here, and I get alpha beta inverse to the p to the n power minus alpha beta inverse. Now this is alpha p to the n, beta inverse p to the n, minus alpha beta inverse. Alpha is a root of the polynomial f, meaning that over here on the side, I'm going to show you that alpha p to the n minus alpha is 0. That's what it means to be a root. So alpha p to the n is equal to alpha. So here, this circled term is alpha. And similarly, beta is a root. So I have beta p to the n power is equal to beta, and I could divide both sides by beta to the p to the n plus 1 power, and I get 1 over beta is 1 over beta to the p to the n power. In other words, this term here is beta inverse. And I'm subtracting alpha beta inverse, therefore I get 0. So what I just showed was, if I start with two roots of this polynomial, two elements on this list, and combine them in this way, I end up with another root, another element on this list, proving that this list is closed under multiplication, and this list contains multiplicative inverses. A similar thing holds for addition. Maybe I should even do subtraction. Let me look at alpha minus beta. So alpha minus beta, that would be alpha minus beta, or actually maybe I could write this as plus negative beta to the p to the n power minus alpha minus beta. Using the freshman's dream, and actually more specifically the corollary to the freshman's dream, this is the same as alpha p to the n power plus negative beta to the p to the n power minus alpha plus beta. So I use the freshman's dream here, because I'm in a field of characteristic p. I'm over ZP. All right, so alpha is a root of my polynomial. So these two terms combine and give me 0. Same thing with beta. P is a prime. If p is 2, so if the prime is 2, then positives and negatives are the same. So if I'm in Z2, then plus 1 and negative 1 are really the same. If I'm not in Z2, if p is another prime, then p is odd, in which case the minus sign is preserved. So the minus sign actually doesn't go away when I raise it to an odd exponent. So these two terms also cancel, and I just end up with 0. So that proves that this list of elements is closed under addition and contains additive inverses. Therefore, these elements are actually a field. I don't need to extend this list to more elements to ensure that I actually have a field. So that actually concludes the proof. I'll write down a sentence writing down what we've done. So the roots of the polynomial f of x are a field without needing to add anything else. Therefore, the splitting field does have the right number of elements. So the splitting field has p to the n elements. All right, wonderful.